All right, well, good evening, everyone, and thank you for joining us for our April Meet the Astronomer with Vanderbilt University Dyer Observatory. I'm Dr. Billy Teets, and I'm the director of the observatory. Tonight, we've got working with us behind the scenes is my colleague Helen Morissette, who's also with me at the Dyer Observatory, and also Brian Smokler of VU News and Communications, who's getting our stream out to you all this evening. I have a couple of announcements before we get into our program. First, if you have questions throughout our program, which we encourage the questions, please make sure that you post those questions in the chat. If you're in full screen mode watching our program, you won't be able to see the chat, so make sure that you exit out of that if you'd like to ask a question. And don't feel like you have to wait to the end to put a question in. As they come to mind, just pop them in the chat and we'll have them ready to go when we do our Q&A session at the end there. Another thing is you'll probably have to be logged in to YouTube in order to use the chat, so you may want to check that out as we're going through some announcements this evening, okay? Let me switch over to a couple of slides here. So in case you didn't see it in our pre-programmed slideshow, we've got a really nice calendar on the Dyer Observatory webpage, dyer.vanderbilt.edu. Alex Rockefeller, one of my other colleagues at the observatory, put that together. Oops, sorry about that. And it's free for download, so make sure that you check that out. Also, yesterday was the Giving Day at Vanderbilt University, and we had a lot of donations come in, and we want to personally thank everyone who donated to the observatory. It's your donations that really help make our outreach and our programming possible, and we cannot thank you enough for giving. And if you'd like to give more, because we're past our Giving Day, but if you'd like to donate some more, we also have a donate button on our website. And like I say, we appreciate any and all donations that we get, because again, it's your support that really helps us with our mission here at the observatory. Not this Saturday, but next Saturday, we will have another one of our virtual star parties. We'll be teaming up with some of our regular colleagues like the Barnard Seaford Astronomical Society, Memphis Astronomical Society, Bays Mountain Park and Planetarium, Rhodes College, and also McGill Science or Space Institute. So hopefully it'll be good and clear that night. We'll be having some viewing and we discussing a bunch of different topics, but if we're clouded out, hey, we're still going to have a great time. So please join us. That's again Saturday, April 18th, or excuse me, 17th at 8 p.m. Central Time, and that is another one of our free programs. And then you may have seen this slide come across your screen and wonder exactly what it is. Well, April 8th, 2024, 3 years from today, we will have the next total solar eclipse passing through the United States. It won't go over Nashville like the 2017 eclipse did, but it's going to pass pretty darn close to our state. In fact, it's going to clip just the very northwestern portion of our state. So the path of totality, as you can see, running through this diagram here, if you're in that very, very deep red area, so right through here, then you're going to see that total solar eclipse. So it's not going to be a long drive in order to enjoy it. We'll have a really nice partial eclipse here in Nashville, but I would highly encourage you to check out the total solar eclipse if possible, because it will change your life. I remember seeing the 2017 eclipse and it was phenomenal. There was nothing else like it that I had seen. So without further ado, I want to switch back over to our speaker for this evening. So our speaker tonight is one of our brand new PhDs from Vanderbilt University, Dr. Laura Vega. So she was born and raised in San Antonio, Texas, and she is a first-generation college graduate who obtained her bachelor's degree in physics from the University of Texas at San Antonio in 2013. She's a former student of the Fisk Vanderbilt Master's to PhD Bridge Program, where she earned her master's degree in physics from Fisk in 2017, and then most recently completed her PhD from Vanderbilt University, defending her thesis in December of last year. She completed her graduate studies at the NASA Harriet Jenkins, NASA Harriet G. Jenkins postdoctoral fellow, and it's a program funded by the NASA Office of STEM Engagements Minority University Research and Education Project. She recently started as a Heising Simmons Foundation postdoctoral fellow at NASA's Goddard Space Flight Center and at the University of Maryland, College Park. Her research focuses on a subclass of supergiant stars that are nearing the ends of their lives, but are also affected by their companion stars. And tonight, she's going to be talking with us about a particularly interesting system called U Monocerotis. So, Dr. Vega, thank you so much for joining us this evening. I'm excited to be able to show off one of our brand new PhDs to our community. So without further ado, please take it away.
Thank you, Billy. That's I'm very excited to share with you my PhD work that I have been doing at Fisk University and Vanderbilt University. I would like to take a moment to tell you about who I am. I will certainly tell you about my title slide here, about this pulsating star, its companion, and its surrounding circumbinary disk. Of course, I will not share all the details of all the pictures that I've showed in the next slide, but just to give you a sense of who I am. So, of course, I got my PhD at UTSA, which is the University of Texas at San Antonio, in physics in December of 2013. I then moved to Nashville to obtain my master's degree in physics from Fisk University. And you can see here where I'm preparing to, nervously preparing to defend my thesis here.
Dr. Vega, can I interrupt for just a second? I don't think the screen is showing.
Oh, the screen is not showing. Okay. I have not shared it, probably. Where am I? Zoom, where is my Zoom? Share screen. I need to put this on presentation mode first, and then share desktop 2. Okay, can you see the title slide?
Yes, we're seeing the presenter view of it, so we can see a little preview of the other slides as well.
Oh, let's see. Stop sharing. Share screen, desktop 2. Share screen. How about now?
Perfect.
Awesome.
All right.
Okay. So this is my title slide, which shows a pulsating star and its stellar companion. And these two stars are orbiting each other within a circumbinary disk, which is just a disk of gas and dust orbiting around these two star systems. But I first wanted to take a moment to just share with you who I am, where I come from. And the next pictures, I won't really talk about every picture I share, but just to give you a sense of who I am. Oops. All right. There we go. So this slide just shows some pictures of, some where I have been, where I'm from. So in this left-hand corner shows me holding my bachelor's degree diploma in physics, which I obtained from UTSA, the University of San Antonio in Texas, in physics. I then moved to Nashville, Tennessee, to join in the master's to PhD bridge program, which I joined in the fall of 2014. And here I am preparing to defend my master's thesis in physics, which was the summer of 2016 in the subject that I will be talking about today. Here I am with my thesis advisor, Dr. Kayvon Stassen, and my mentor, Dr. Rudy Montes, who happens to be also from San Antonio, Texas. And I'm showing here a poster of my research. I also want to give thanks to my NASA mentor, Dr. Patty Boyd, who has been very helpful throughout this journey. And I'm very grateful for, well, actually, I'm very grateful to NASA that has funded this research from the start, since the master's phase all the way to the end. And without further ado, let's get started. So first, I want to start off with physics. What is physics? Well, it's the understanding of the natural world around us, whether it's momentum and the energy that we see in other systems, looking at the fluid dynamics of a soccer ball going through a field of gas, or gravitation, which governs all of the stars and actually galaxies in the universe. And we take this understanding of physics into astrophysics and cosmology, which helps us understand the interactions of galaxies themselves, perhaps supergiant stars and black holes, how they interact, how baby stars are formed in huge clouds of gas and dust, as shown in this GIF right here, or pulsating stars nearing the end of their lives, or even planets orbiting stars around other systems, and even gas and stars or dark matter, how they form these filaments in the large grand structure of the universe. My focus is on pulsating stars, dying stars. So here is a diagram of stars as they are the least massive all the way to the most massive stars. And this GIF shows how they are born in huge clouds of gas and dust. And depending on their mass, determines their ultimate fate as they go throughout their lives. My focus is on solar mass type stars. So stars that evolve around the same mass of the star, of the solar mass star. And as they evolve towards red giant phases, they expand more and they become fluffier. So this stellar mass is fluffier, and eventually they become unstable towards the end of their lives. And for the sun in particular, the sun has been making or producing helium atoms from hydrogen atoms for about 5 billion years. And it will continue to do so for another 5 billion years more. But eventually, when that generation stops, the star will experience changes in its inner physics, and it will swell up into red giant dimensions and eventually start pulsating, as you can see here in the diagram. And this is kind of like a tug of war between pressure and gravity. And eventually they become planetary nebula, which I will show later some beautiful images from Hubble. But as these outer shells of the star expand, they're not as bound to the gravitational pull of the star. So they're just so spread out that they expand out into space. And eventually you just get the core of the star, which is the white dwarf. That's just the bare, naked core of a star. So this is a diagram. It's called the Hertzsprung-Russell diagram. And it's a very popular diagram amongst astronomers that is very helpful for us to know the luminosity, the relationship between the luminosity and temperature of a star. So stars like the sun live happily their lives making hydrogen atoms into helium atoms in their core. But eventually that process stops. And when that stops, they experience changes, and that heat expands the outer layers of the star, making them into supergiant stars, and eventually even supergiant stars, where my focus is when they're about to release those outer layers of their stars, of the outer layers. So they are pulsating, they're emitting this really hot, dense gas in the middle, and releasing their carbon and oxygen layers out. So to get a sense of what I'm talking about, here is an illustration of the sun compared to the planets that orbit around this star. The sun is a star. And if we take this little dot right there as our Earth, if we were to fill the sun with a bunch of Earths, it would take 1 million Earths to fill the sun. Now, when we are talking about evolved stars, these are evolved stars that have expanded so much due to the radiation pressure generated between the end stages of these stars, that they become more expanded. So if we take this little point there, that represents our sun now. There are actually stars that are at a very larger scales, even 100 times, 1,000 times the radius of the sun. But all of this material, like this radius, is so loose that they expand more and more towards space and eventually become planetary nebula, at least for stars like the sun. So here I'm showing some beautiful pictures from Hubble, where this outer stellar emission is coming from the end stages of the star, and these are called planetary nebula. However, we see that they have very different shapes and sizes and not so much spherical. So what is happening? Well, we don't really know. What we think is happening is that perhaps there are stellar winds that are not perhaps uniform, even magnetic fields around these stars that are making these weird shapes around them. And another key ingredient might be binarity. So binarity means that there is actually a companion star influencing all of that matter, all of that stellar emission out into space. So you have these two stars orbiting each other. One of them has already been evolved, and this companion is influencing that material into outer space. So we see these weird shapes happening. So that is a planetary nebula. And the next slide that I want to show you is, how do astronomers figure out what is happening with these stars? Like, how do we know? Well, because we cannot travel to these stars, they're just so far away, we rely on light, on radiation, on different types of light that the universe has. So this diagram shows gamma rays through X-rays, ultraviolet, visible, infrared, and radio. So this spectrum is all the different types of light that we can detect. Our eyes are detectors. So we can only detect that little piece of the rainbow in between the ultraviolet and infrared light. So that's what we can detect. But there's actually all these types of radiation, from gamma to radio waves, and a short wavelength of a gamma ray is from one peak to the other. A long wavelength would be from, for example, for this peak to the other peak. And to compare these wavelength sizes, so for example, gamma rays are the size of atomic nuclei. So for example, the atomic nuclei in a hydrogen atom, so just the proton, that's how short these wavelengths are. Of course, these wavelengths are all invisible to us. And it goes all the way to the wavelength sizes of a building. So these wavelengths could be as large as a building. And these are called radio waves. And so to give some live examples, I'm going to show you the examples of bees. So these bumblebees can actually see an ultraviolet light, which is really cool, which helps them find pollen and nectar in flowers. So this is an example of what our eyes can detect. Our detectors can detect visible light, but the vision of bumblebees can detect ultraviolet light, which has more information of what the patterns of a flower can have. So it's actually kind of saying like, yeah, this flower is like, here is the nectar, come take your food. Of course, humans cannot see ultraviolet light, but we can certainly feel it because the sun can give ultraviolet rays. And so it's very important to have sunblock so that we could be protected from those ultraviolet rays, because yeah, they're very harmful for us. So it's just a little helpful reminder. Another example is snakes. Snakes can detect their vision is infrared light, and they can detect infrared emission. And of course, humans, rodents, little mice, other mammals emit an infrared light, and so snakes can detect that in the night. So here's an example of a man who is holding a bag around his arm. But if we were to have detectors, infrared detectors, we would be able to see through that black plastic bag. And so snakes have the capability of looking through that bag if they wanted to. So it's the same thing as if they wanted to spot for lunch in the night sky, or in the woods, they would be able to find a little mouse hiding behind the bush, because mice and warm creatures emit infrared light, and snakes could detect it. Now, going into larger grand scales, astronomers use different detectors to see the universe in different light. So here I have an example of the Crab supernova. So a supernova is an explosion of a dead star. So I'm here, let's see if I could play it. Okay, there it is. So you will see that a star has gone supernova. That's an explosion. And this happens to really massive stars. And these supernova happen in all kinds of shapes and morphologies. And in order to understand what's happening, we use detectors such as Chandra, which can observe the night sky in X-ray. XMM Newton can observe the night sky in X-ray and ultraviolet, but here we show an ultraviolet image. Hubble can see it in optical, Spitzer in infrared, and these radio antenna that are on the ground on the Earth in radio wavelengths. So the next slide, I'm gonna pop up a what it's called a chat bomb. So I'm gonna ask you, which light wave can we humans see? So is it X-ray, radio, optical, or infrared? And so I'm gonna give folks a couple of seconds before you pop in your questions. I'm gonna say go. Actually, I haven't really practiced this, but let's see. Billy,
Yeah, I'm monitoring the chat there.
okay.
All right.
So,
oh, you got it right there.
Okay. So which light wave can humans see? Is it X-ray, radio, optical, or infrared? So yeah, we're seeing a C, optical, yep. Awesome. Yeah, so we can see, our eyes can see optical wavelengths, and which is analogous to visible wavelengths. Go back to my slide here. So Hubble actually can see optical wavelengths and ultraviolet wavelengths, which is very helpful for astronomers. So now I'm going to switch over to all of the telescopes that I have used in order to understand the types of stars that I study. So here we have, the Kepler telescope and the XMM Newton, Gaia, the submillimeter array, which observes the sky in radio wavelengths, the American Astronomical Star Observers, which they observe the night sky from optical wavelengths, and glass plates that were actually made in the early 1800s. So the stars that I study, let's first introduce RV Tauri. So RV Tauri, which is shown right here, is a very bright star. It's in the constellation of Taurus, and its characteristic feature is that it shows these alternating deep and shallow minima in its brightness. So as it's pulsating, it has this very distinct pulsation period. And right now, I'm gonna go over to our model of the night sky. It's called Stellarium. You could actually download it if you want to. We're gonna look for RV Tau, which is right there. It's located there. Let's turn on some constellations and the names of constellations and perhaps some artwork. So there we go. So RV Tau, so actually, we are looking west in the night sky. And RV Tau is actually on the Taurus constellation, just right, let's see, east, oops, let's look for RV Tau again. Okay, so RV Tau is a bright supergiant star. Of course, you might need a telescope or some binoculars to observe it, but it's a pulsating star that has this characteristic feature of alternating deep and shallow minima due to its pulsation. So let's go back to our presentation. And so there is a class of stars named after this star because they show similar characteristics to this star. So there's actually a class of RV Tau stars named after RV Tau. They are luminous pulsating supergiant stars. They're relatively cool, between 5,000 Kelvin to 6,000 Kelvin, which, what does that even mean? So let's check our, okay, so what does 5,000 Kelvin mean? So that means that it's 8,540 Fahrenheit. That's still pretty hot, but in the terms of stars, that's relatively cool. It's a relatively cool star. And we know that they are in binary systems. So this diagram on the right-hand side is again a diagram that astronomers use very much, that shows the brightness of a star compared to its temperature. And so stars like the sun, which is shown here, eventually evolve in luminosity. They get brighter and cooler, and eventually become stars in that region where the RV Tau stars are located. But there are stars that are massive enough that have evolutionary stages that also go into that region of the luminosity and temperature space. So we really don't know if RV Tau stars come from stars like the sun, or perhaps stars that are more massive than the sun. So that's a question that we still are trying to figure out. What we do know is that RV Tau stars are type 2 Cepheids. So a Cepheid variable is a star that has a pulsation period that is between 10 days and 100 days. So we know that this relationship between the luminosity and its period is pretty constant. And thanks to Henrietta Leavitt, which she discovered this relationship between the luminosity and the period of a star, we are able to know that there is actually a relationship between the luminosity and the period, and this can further help us determine the distance of these stars, whether they're in the Milky Way galaxy, which we are living in, or perhaps in other galaxies in the Large Magellanic Cloud, the Andromeda Galaxy, or other galaxies. So this is a very powerful tool that we know that can help us. So here again, I just show the how, so the y-axis is the luminosity of a star, and the x-axis is the temperature, where the temperature goes from hot to cool. And the RV Tau stars are located in a rather luminous state and cool state. But we don't really know where they come from. Are they coming from massive stars? Are they coming from sun-like stars? Now, there are two types of RV tau variable stars. So the regular RV tau stars show this alternating shallow, deep pattern in their brightness. However, actually, these patterns can be ranged between 20 days and a couple months. So the pulsation periods can vary between 20 days and a few months as they pulsate out and in, out and in. However, there's an actual a type 2 RBB type star that show this longer term variation. Of course, it's kind of hard to tell this long-term variation. All of these points are measurements of brightness over time, over years of time. So it's kind of easier to see data like this. So the RVB show this longer term variation. So you can see the pulsations clearly. There's this longer term variation happening. And up to recently, we didn't really know what was causing that variation. And so I will show you next an animation that was produced by NASA. So I was in communication with NASA folks, especially with Chris J. Smith at NASA Goddard. NASA Goddard is located in Greenbelt, Maryland. And Chris was very patient with me. And when I was trying to explain, okay, these stars are pulsating, they have a stellar companion, and they are within a really dusty disk of gas and dust. And he did a phenomenal job. And so here it is. Here is a pulsating star, which is about 100 times as luminous as the sun. And in the background, you can see its stellar companion and the dusty disk that is around the stellar system. So that is what an RV tau type star looks like. And so in 2017, not long ago, we were able to publish an article on the Astrophysical Journal. And we looked at the RVB type star, DF Cygni. This is the title of the article, and here are the authors. So DF Cygni has a relatively cool temperature, 4,840 Kelvin. Its pulsation period is about 50 days. Its RVB period is about 780 days. And its binary orbit is also about 780 days, which is interesting because the long-term period, the photometric period, is very similar to the binary period of the system. So to go into Kepler. So Kepler, the spacecraft was launched in 2009. And the main mission of Kepler was to find exoplanets around other stars using the transit method. And so the transit, oh, it's not showing here. Okay, so the transit method is that a planet goes in front of the star, and as that planet transits in front of the star, it shows a dip in brightness of the star. And depending on the size of the planet shows the size of the dip. And Kepler observed the star field near Cygnus and Lyra. And so here is the, actually, here we go. So this is the instrument that observed that patch of the sky. And so right now I'm gonna go over to our Stellarium software, which by the way, you can actually download on your computer and use if you want to. So let's look for DF Cygni, DF Sig. Okay, it's actually has not risen yet. So let's here fast forward our time. Let's fast forward it more. How about more? And pause. Okay, there we go. So we are looking at northeast, and DF Cygni is located here in the northeast sky. And let's turn on some constellations so that you can see where DF Cygni is located. So it's located in the Cygnus constellation. And if we turn on our artwork, there we go. There you see this swan shape that depicts Cygnus. And when we turn on show exoplanets, that is the star field that Kepler observed. So Kepler observed this particular patch of sky for 4 long years, taking an image every 30 minutes. So that's a lot of data. So that's why we can see a lot of exoplanets were discovered in this region of the sky. So if we take that away, so here is a DF Cygni. So DF Cygni is the star that we are interested in. So DF Cygni was the only orbital star in the Kepler field of view, which was very interesting. So what happens is that Kepler has these CCD cameras that observe the night sky. And with that information, it gets translated over into brightness over time. And what Kepler did was try to find planets orbiting other stars. And so it, depending on 3 to 4 orbits, makes it a candidate or a confirmed planet in order to find a planet orbiting another star. But not only did Kepler find other planets around other stars, it also measured the brightness variations of a variety of different stars that didn't have planets. For example, DF Cygni. And so the next slide shows this brightness variation of DF Cygni over those 4 long years. And you can see the pulsations of DF Cygni over time. And this long-term variation. So as you can see, these amplitudes are rather large at maximum light. But then when it goes into minimum light, they're not as large. And in this project, we showed that there is something going on. We found that these amplitudes at maximum brightness are actually the same as these little amplitudes at minimum brightness. But the only difference was that something was blocking those amplitudes. So there is maybe some sort of disk or gas and dust blocking those amplitudes from the pulsating star. And so in this publication or in this work, we were able to describe that the pulsation amplitudes are actually the same. They're the same throughout the whole light curve, but there is something blocking those amplitudes. And I will show later what that looks like. So in this slide, I just wanted to introduce the digital sky access to a century of sky from Harvard, which is called DASH. So this is here a glass plate which was observed by Harvard computers. And Harvard computers were actually female astronomers that looked at these glass plates throughout time. And they measured the brightnesses of the stars in these glass plates. So the background plate here shows where Yuman was located, and this red circle here shows where Yuman is. And when these Harvard astronomers measured these brightnesses, they were able to record them in a logbook, which is showed here in the bottom right corner. And they measured the brightness of these stars as well as the time of those brightnesses. And they used these tools here. Actually, I went to the Harvard College maybe in 2018, and there was a really awesome display of the glass plates and some reading materials and some images where we can learn about how these astronomers did their work. And here in this glass plate, you can see that it's a bit chipped. It was kind of broken, I guess. And all of these notations means the recordings of the brightnesses of these stars in this star field. And this middle panel shows some images of Jupiter. So they observed the whole sky and was very awesome. The next slide, I want to introduce the American Association of Variable Star Observers. So it's a global network of amateur and professional astronomers dedicated to monitoring variable stars, so stars that vary in brightness, since the late 1800s. So that's over 100 years ago. That's more than 100 years ago. And so they used their eyes, or perhaps binoculars and telescopes, to measure the brightnesses of these stars that just vary in brightness. And this here, this image is from the group that gathered together, I think in 2019, and just to talk about astronomy, how to use a telescope, what they found, all interesting things. The next slide I'm going to show is, okay, so the top panel is the data from Kepler. Of course, Kepler is above it's above the Earth, which can detect light in a much more better way. And telescopes on the ground, of course, they have to kind of fight against the atmosphere that the Earth has between the telescope and the sky. But still, you can see, for example, on Kepler, how the large variations you can see here, how they are throughout time. And getting more data. All of these points are actually observations from photographic plates from Dash all the way back into like 1880. I'm showing the long-term variation of DF Cygni. So this is how powerful observing these stars are to just our short human lifetime. So this is very cool. The next star that I want to talk about is U Monocerotis. So Yuman is a star that is located in the Monocerotis constellation. So let's go back to our Stellarium software here and look for Yuman. Actually, you could you could download this software. Oops, okay. You could download this software on your computer if you want to, and it's really fun to play with. Where is Yuman? Let's look for Yuman. So we are, let's get rid of the ground. Okay, we're peering through the ground. But anyway, so Monocerotis is near Orion. So it's located right near the, I guess, the feet of the unicorn. So that's where Yuman is located. Okay, back to our presentation. So we published an article recently, actually last month. And here are some facts about Yuman. So it's the second brightest star, second brightest orbital star in the night sky. Its temperature is about 5,000 Kelvin. Its RVB long-term period is about 2,450 days, which is about 6 years, 6 and such years for it to orbit around its star, around its companion. And its distance is about 1.1 kiloparsecs, which means it's about 3,600 light years away. That means that the light from Yuman takes about 3,000 light years or years to come to us, to Earth, to be detected. That's how far away it is. Its pulsation is about 46 days. Luminosity, 5,000 times the luminosity of the sun. And it's about 100 times the radius of the sun. So it's really, really extended. And here is an image of Yuman in an optical image. And here we have an animation that I had coordinated with Chris. And when I told him, I'm like, well, we have this pulsating star and it has a stellar companion and it's surrounded by a stellar disk. So here it is. And throughout its orbit, it's actually being blocked by the inner edge of the disk. So here, as it being blocked, that is what causes the amplitude to get shorter. But the pulsation amplitudes are always the same. It's just something is blocking those pulsation amplitudes. And we now know that it's a disk or some screen blocking those pulsations. So we also found the orbital motion of Yuman based on looking at its spectrum. So I won't go too deep into this, but when a So when we observe a star throughout its orbit, we see that the spectrum shifts in a certain way. And when it shifts, we can note that and find where in its orbit it's at. And from this information, we can find orbital parameters such as the inclination, how inclined it's its orbit, the mass of the star, how intrinsic it is. So intrinsic means like how stretched out is its orbit around the other star. So with all of these information, we can find that the stellar companion is about 2 times the mass of the sun. And with a little bit more math, we can find that it is about 6 AU in separation. So 1 AU is the separation from the sun to Earth. So times that 6 times, that's about a little larger than the sun to Jupiter. That's how distant they are to each other. And again, we here show the data, the observations from DASH, from the photographic plates, and from observations from AAVSO astronomers that have observed this system from the late 1880s. And we can see that the long-term variation in very clearly. So what we did was a little bit of math to kind of align both of these data sets to see the long-term variation happen from the early 1880s. Of course, it's more defined in the AAVSO data because there's more astronomers looking at this star. So let's check out where the AAVSO and DASH data align the most. So AAVSO data are in purple and the DASH data are in teal. Of course, they're not super aligned, but they're close. And here we are just trying to figure out how they align in time. And this model just represents how boxy the long-term variation looks like. And in order to see the disk or the how the disk is behaving, we try to subtract the pulsations. And so in this bottom panel, we show the pulsation or the long-term trend of the disk. And we see that the long-term trend kind of disappears at least twice in the past. And in the next image, it shows that it has a deeper minimum at some point in time, but it also shows that that deep minimum in the long-term trend is not as apparent. So how we astronomers interpret it is that there is some sort of warp in the disk. So here is the binary star right there in the center, and there is this warp happening, which is magnified here. So here's the binary star. There's some warp happening. At some points, it's actually dimming the brightness of the stars more, but at other times, it's not as much. So That's why we think there is some sort of warp in the binary system that is going around it. So now we are here with submillimeter array data. So the submillimeter array is an 8 telescope interferometer, which is just a network of 8 telescopes that look at the sky in radio wavelengths. And we were able to image the sky with this awesome interferometer. And here is the image located in the right-hand corner. So we think that this extent is the actual disk of the RV Tau star. And so with the image of the SMA data and some information from Gaia, we can kind of estimate what the disk size is, which we think it's 550 AU, which is 550 times the distance from the sun to the Earth. So to better explain that, we have here the binary system and then the extent of the disk, and that is 550 AU. Of course, the distance from the sun to Neptune is this. Voyager to from the sun to Voyager is this, and this is the maximum radius of this disk. So it's very spread out, and we think that the material of this disk actually came from the pulsating star as it evolved. I know we're running out of time, so let's go to the X-ray images. So XMM Newton was able to look at Yuman. And the cool thing about X-rays is that you get, so XMM Newton, you can get data tables of position, time, and energy, so that you can get data in image, so the position of these stars in the detectors, the XY position in the detectors, as well as the time of those photons arriving at the detectors and their energies, how energetic they are as they arrive at the detectors, to also get a spectrum of the energy and the wavelength. So then this next image is where Yuman is located in the, it's an image of XMM Newton and where we think Yuman is located. And of course, when we grab those photons, we can actually assess the spectrum, because we can see what energy they are when they arrived on the detector, and how energetic they are. So that's represented here. We modeled these energetic photons, and we assessed that this X-ray emission is about 10 megakelvin emission. We still do not know where it's coming from, but based on the collaboration and other studies from other colleagues in Europe, we think that this emission is coming from the companion star. And so here I'm going to play an image of the companion star where it's accreting material and making its own little disk around the star. And you can see the pulsating star in the background. And so this is sort of where we are at now. Of course, we need more information to understand what's going on. But this is where the top of the line theory is on orbital stars right now. And just to finish up, we were able to find X-ray emission from orbital stars, which is the first time for any orbital star. We observed optical data, radio data, in order to kind of define what we think is going on in these type of stars. But it could turn out that they may not look like this. They may look very different. So we just need more data to understand what is really happening. And so the future of understanding orbital stars, so a pulsating star and a companion star surrounded by this disk of gas and dust, can be probably moved to, there we go, TESS data. So TESS is looking at the sky at a very resolved resolution. And so here I have an example of the pulsations of Yuman, and showing the observations of TESS that show just a peak of what TESS can resolve. But hopefully someday we can see what is really happening with these evolved stars. So with that, I'm gonna open it up to questions. I'm sure there's some clarifying questions that I kind of glossed over.
Well, thank you very much, Laura. That was a phenomenal presentation. It's really cool to be able to see how we've been able to take all this data over all these years, or I should say how you've been able to take this data from all these years and use it to put together a more complete picture, and not just in visible light, but in all these different types of light. I know that when we're giving tours at the observatory, or I'm lecturing in a class, one of the key things we try to convey is that it's not just about the type of light that you can see, it's the type of light that you can't see that can tell you so much more about what's going on. So this is a great example of how you're able to tie not only two types of light, but multiple types of light together to really give us that complete picture. So excellent job, and we got a lot of great comments from the chat as well. So excellent presentation. There was a question that came up when you were talking about the disk. Do astronomers think that planets will be able to form out of this disk, or maybe is this star system evolving too much and that would disrupt that, or what are your thoughts on that?
I do know that there are post-AGB, so evolved stars that have these disks around them that have been forming disks, at least some detections of planets. We still don't know, but it seems like there are some detections of planets around these evolved stars.
Okay.
From these disks.
And actually, I had a question. So when you're, so when you're talking about the supergiant and it's pulsating, when it changes its size and gets bigger and smaller, does it dramatically change its size? Like, does it get 10 times bigger, or does it maybe get about 1.5 times its size, or can you comment on that?
It does get relatively larger in size, for sure. Mm-hmm. So these are supergiant stars that actually take time to expand. They take maybe 20 to 30 days, maybe even 100 days to actually go, as far as they can go, and then come back down.
Okay.
So yeah, takes a long for orbital stars, yes, they do take a while to expand.
But when they expand, do they essentially double their size, or get 10 times their size, or is it maybe just like, you know, maybe a 20% increase in their size?
Actually, I do not know the answer to that question, but I'm assuming they do relatively expand largely in their size. Yeah, because these are type 2 Cepheid variables, and they are at the more brighter stages of the period luminosity diagram. So I'm assuming they do become larger than, perhaps 20% or larger than the contracted size.
Gotcha. Okay. Let's see. Dr. Grunstrom asks, what kinds of observations are you hoping for in the future? Especially in your dreams. What kind of observations would you like to be able to make if you had your pick?
Definitely more X-ray data. I know that my mentor, Dr. Rudy Montes, and his students are kind of mining the older data that is available now, but hopefully there will be data in X-ray to just kind of pinpoint where those X-rays are coming from. Are they coming from the companion star? Are they coming from the pulsating star? Or perhaps the interaction between the two stars or the disk surrounding them? Definitely X-rays. X-rays.
I was wondering, kind of along these lines, I guess you may have covered this in your lecture and I missed it. When the pulsating star is blocked by that disk, do you know the last time that happened, roughly speaking?
I think. Let's see.
But
can you see my image here? So it's about, let's see, 2, 4, 6, 8. Maybe 2018.
Okay.
So right now it's actually at maximum light.
Okay.
Yuman.
I was just wondering if there would be more infrared observations, because you've got the radio data that shows that there should be a big disk there, and it's looks like it's the disk that's causing that deep minimum for that long period of time. And I was just wondering if infrared might show some if you observe the system in infrared, if you would see the same decrease in infrared as you would in say visible light, because infrared's able to get through the dust better, so it shouldn't be hindered as much, I wouldn't think. But the visible light would be hindered as much. So I was just wondering, maybe if you saw a deep dip because the star is being hidden by the disk, if you wouldn't see as much of a dip in the infrared. But I don't suppose, has anybody observed that in infrared that you know of?
So there are certainly some observations happening right now that might make my observations, or I guess my claims, kind of outdated. So look out for that.
Okay.
Definitely, yes.
All right. Let's see. I think that there's one more question that popped in my head. When you're talking about how we're seeing this regular brightness variation, about how much does this star change in apparent magnitude? So, I mean, would it be something where I could look at it in a telescope one night and say, okay, it's this brightness, and then when it's at minimum, say, oh yeah, I can definitely see a huge drop in brightness? Or is it more of a subtle thing that you'd really have to have like a camera to be able to pick out?
I think for Yuman, you would be able to see Yuman with perhaps some binoculars at maximum brightness.
Mhm.
But yeah, when it's going, when it's at its deeper long-term minimum, yeah, you'll need some telescopes. So
definitely a noticeable thing. Okay.
Yep, definitely.
Gotcha. Let's see. Will there be any full spectrometry to understand the composition of the disk?
I think so. But Yuman is a very attractive star right now. I'm actually working with a group that are trying to wrap up some really recent results, which I can't really talk about right now, but
Gotcha.
yep, definitely.
But good,
Yes.
but more things to come, right?
Yes, yes.
Alrighty. I think that may have been all of the questions. Oh, wait, hold on one second here. Can you explain the difference between the RVB period and the orbital period? And one follow-up to that is there a spectral type of the companion star?
So I can certainly show, let's see. So can you see those two stars orbiting each other?
Yes.
Okay. So actually, the orbital period is the photometric period. And that's something that we learned recently, is that when the pulsating star comes behind the inner edge of the disk, that is actually when the pulsating star comes behind the disk. And when the pulsations look, minimum, however, of course, they're actually the same pulsations, but the RVB photometric period is essentially a binary phenomenon. And for the companion star, we still really don't know what is composed of. We know that it's there because the pulsating star shows some radial velocity. Can't do it anymore. We know that it's there because the pulsating star shows some radial velocity movement there. But yeah, we think that it's a main sequence star, perhaps a 2 solar mass main sequence star, but yeah, we don't really know what it is.
So I guess if I remember correctly, I think Sirius A is around 2 solar masses. So I think it's like an A star or something like that. That's definitely hotter.
Probably an A star.
Is it basically that the pulsating star is just so much brighter that it's hard to see the companion because of the glare of that star?
Yeah, definitely. The pulsating star, in the case of Yuman, is about 100 times, well, actually, I think it was like 5,000 times luminous as the sun.
Okay. All righty. Well, let's see. I haven't seen a question pop up in about a minute or so. So I think that might actually be the end of the questions. I keep saying that, and then another one pops in there. But Dr. Vega, thank you so much for joining us this evening. This was a fascinating talk, and again, we got lots of great comments. There was someone who had a son that was watching this and was completely enamored with this talk. So thank you for sharing with us your research and this ongoing research, I should say. So we look forward to seeing your name in publications to come and learn more about some of the great things you're going to be doing. So thank you again for joining us this evening.
I'm very happy to be here. Thank you, Billy.
All right, and congratulations on the new PhD.
Thanks.
Alrighty. So we are about 8:20 now. So I want to thank everybody for joining us this evening. We haven't lined up a speaker yet for our May Meet the Astronomer but we'll certainly be doing that, and we'll definitely let you know. We'll send out some reminder emails and definitely post it on our website. So I'd also like to thank, again, Brian Smokler and Helen Morissette, who's been helping out this evening. And thank you all for joining us. And again, thanks to everyone who has who provided donations over the years. And thanks for the donations for the Giving Day yesterday. Again, we couldn't have done what we've been doing without your support. And we really appreciate you all from the bottom of our hearts. So remember next Saturday, I forget the date, not as in 2 days, but is in a little over a week from now, starting at 8 p.m. Central Time, we will be holding our April virtual star party. And again, that's free. There's a link on the front page of our website, so we hope that you can join us. And that's going to be interactive as well. So as we go through and do discussions about different topics and hopefully are doing some viewing, we really want you all to be sure to post questions. And if you have suggestions as well during the program for future programs, we'd love to hear those as well. So I hope to see you all Saturday night. Hope everyone has a great weekend, and we will see you next time.